Assalamu alaikum. This is lecture 25 of data security and encryption, and in this lecture I am going to discuss about the digital signature. The most important development in the form of work on public key cryptography is the digital signature. The digital signature provides a set of security capabilities that would be difficult to implement in any other way. So here are the lecture content. In this lecture I am going to discuss about the digital signature properties. There will be some different kind of attacks and forgeries that will be discussed, and digital signature requirements will be analyzed, and there will be some algorithm techniques to build the digital signatures, and two famous techniques are referred as Elgamal and Schnorr digital signature schemes. Then there will be a NIST digital signature algorithm and a elliptic curve digital signature algorithm. And finally, there will be an RSA-PSS digital signature algorithm and its implementation and signing and verification signatures. So this figure shows a generic model of the process of constructing and using the digital signatures. All of the digital signature schemes discussed in this lecture have this structure. So for example, that a user Bob wants to send a message to Alice, although it is not important that the message to be kept secret. He wants Alice to be certain that the message is indeed sent from the Bob. For this purpose, Bob uses a secure hash function such as SHA-512 to generate a hash value for the message. That hash value, together with the Bob's private key, serves as an input to a digital signature algorithm, which produces a short block of the function as a digital signature. Bob sends the message with the signature attached. When Alice receives the message plus the signature, she first calculates the hash value for the message and then calculates the provides the hash value and the Bob's public key as input to digital signature algorithm, which verifies that the signature is authentic or not. So if the algorithm returns the result that the signature is valid, Alice is confirmed that the message must have been signed by the Bob. So no one else has the Bob's private key, and therefore no one else could have created the signature that could be verified for this message with the Bob's public key. So in addition, it is impossible to alter the message without the access to the Bob's private key, so the message is authenticated both in terms of source and in terms of data integrity. Message authentication protocols protect two parties from the third party. However, it does not protect the two parties against each other. Several forms of dispute between the two parties are possible. So in situation where there is no complete trust between sender and receiver, something more than authentication is needed. The most attractive solution is this problem is the digital signature. The digital signature must have the following properties: that it must verify the author and the date and the time of the signature. It must authenticate the contents of the signature, and it must be verifiable by third parties to resolve dispute. Therefore, a digital signature function includes the authentication functions. So several authors list the following types of attack in order of increasing severity. Here, A is denoted by the user whose signature method is being attacked, and C denotes the attacker. So the first type of attack on digital signature is key only attack, and in this case attacker only knows A's public key. The second type of attack is known message attack. and in this case the attacker chooses a list of messages before attempting to break A's signature scheme, independent of A's public key. C attacker then obtains the A valid signature for chosen messages. The attack is generic because it does not depend on A's public key. The same attack is used against everyone. The fourth kind of attack is directed chosen message attack. It is similar to the generic attack except that the list of messages to be signed is chosen after the attacker knows is public key but any signatures are seen. So the final attack is adaptive chosen message attack. In this case, attacker is allowed to use A's as an oracle. This means that the attacker may request A signatures of messages that depend on the previously obtained messages signature pairs. Similarly, authors then defines success at breaking signature schemes as an outcome in which attacker can do any of the following with non-negligible property. The first one is total break, which means that the attacker determines a private key. The second forgery can be universal forgery. An attacker finds an efficient signing algorithm that provides an equivalent way of constructing signatures on arbitrary messages. Selective forgery states that the attacker forges a signature for a particular message chosen by C. Existential forgery refers attacker forges a signature for that at least one message is the attacker has no control over the messages. So on the basis of properties and attacks just discussed, we can formulate the following requirements for a digital signature. A digital signature must be a bit pattern that depends on the message being signed. The digital signature must use some information only known to the sender to prevent both forgery and denial attacks. It must be relatively easy to produce digital signature, and it must be relatively easy to recognize and verify the digital signature. It must be computationally infeasible to forge a digital signature either by constructing a new message or existing digital signature, or by constructing a fraudulent digital signature for given message. It must be practical to retain a copy of digital signature storage. Therefore, a secure hash function embedded in a scheme provides a basis for satisfying these requirements. However, care must be taken in the design of the details of the scheme. So the term digital signature refers to the digital signature scheme that involves only communicating proper parties. It is assumed that the destination knows the public key of the source. Similarly, confidentiality can be provided by encrypting the entire message plus the signature with a shared key. It is important to perform the signature function first and then outer confidentiality function. So in cases of dispute between some third party must view the message and its signature. Finally, the validity of the scheme depends on the security of sender's private key. So if the sender later wishes to deny the sending a particular message, then the sender can claim that the private key was lost or stolen and then someone else forged his or her signature. One way to thwart or at least weaken this ploy is to require every signed message to include a timestamp and to require prompt reporting of compromised keys to a central authority. So one example to require every signed message to include timestamp. The another threat is that a private key might actually be stolen from X at a time. The universally accepted technique for dealing with these threats is the use of digital signatures and digital certificates and certificate authorities, which will be discussed in the upcoming lectures. So before examining the NIST digital signature algorithms, it is helpful to understand the Elgamal and Schnorr digital signature schemes. If you recall that the Elgamal encryption scheme is designed to enable encryption by user's public key with the decryption of the user's private key. So global elements are a prime number q and a, which is a primitive root of q, and it uses the private key for encryption, signing of the digital signature, and it uses the public key for decryption and the verification of the digital signature. So each user generates their key and it chooses a secret key number from 1 to q minus 1, and it computes their public key is equal to y of a is equal to a raised to power x of a mod q. Similarly, as with the Elgamal digital signature, the Schnorr digital scheme is based on discrete logarithms, and it minimizes the message dependent amount of computation required to generate a signature by multiplying a 2n bit integer with an n bit integer. The main work of the Schnorr digital signature can be done during the idle time of the processor. Based on using the prime modulus p with the p minus 1 having the prime factor q of the appropriate size, a typical p is a 1024-bit number and q is a 160-bit number. Finally, the digital signature algorithm is proposed by the NIST, and it was published as a Federal Information Processing Standard FIPS A186, and it makes use of a secure hash algorithm. So DSA was originally proposed in 1991 and revised in 1993 in response to the public feedback concerning the security of the scheme. There was a further minor revision in 1996. In 2000, an expanded version of the standard was issued, while FIPS 186-2 subsequently updated to FIPS-3 in 2009 and version 4 in 2003. So latest version is 2013 version and also incorporates the digital signature algorithm based on RSA and on elliptic curve cryptography. So the DSA uses an algorithm that is designed to provide only the digital signature function. Unlike RSA, it cannot be used for encryption or key exchange. Nevertheless, it is a public key scheme. So this figure contrasts two approaches, the DSA approach and the RSA approach, for generating digital signatures that are used in both approaches. So in the first case, the RSA approach, the message to be signed is input to a hash function that produces a secure hash code of fixed length. This hash code is then encrypted using the sender's private key PRFA to form the signature, both the message and signature, and then transmitted. The recipient uses the signature using the sender's public key. So if the calculated hash code matches the decrypted signature, the signature is accepted as valid. Because only the sender knows the private key, only the sender could have produced the valid signature. On the other hand, the DSA approach also makes use of the hash function. The hash code is provided as input to the signature function along with a random number k generated for the particular signature. The signature function also depends on the sender's private key PRFA and the set of parameters known as a group of communicating principal. We can consider this set of constitutes to a global public key PUG. The result is signature consisting of two components labeled as S and R along with the message M. So at the receiving end, the hash code of the incoming message is generated. The hash code and the signature are input to a verification function, and the verification function also depends on the global public key as well as the sender's public key, which is paired with the sender's private key. The output of the verification function is a value that is equal to signature component or the signature is valid. The signature function is such a way is such that only the sender with the knowledge of the private key could have produced the valid signature. So the DSA digital signature algorithm is based on the difficulty of computing discrete logarithm, and it is based on schemes of originally presented by Elgamal and Schnorr. So this figure summarizes the algorithm. There are three parameters that are public and can be a group of users, can be common to a group of users. An n-bit prime number q is chosen and a prime number p is selected with the length between 512 and 1024 bits in the increments of 64 bits. The variable g is chosen from the form of a hash function to the p minus 1 over q mod p, where h is an integer between 1 and p minus 1. So with the restriction that g must be greater than 1. So with these three parameters in hand, each user selects the private key and generates the public key. The public key is calculated in the form of from the private key as y is equal to g of x mod p. So the signature message M consists of the pair of numbers R and S, which are function of the public key components P, Q, G and the user's private key, hash code of the message and the additional integer K that should be generated randomly or pseudo-randomly and be unique in each signing. Therefore, M, R dash and S dash can be received versions of message and the signatures respectively. Verification is performed using the formulas shown here for W, U1, U2 and V, and you test that the verification is valid received signature. The receiver generates the quantity V that is the function of the public key components, the sender's public key, the hash code of the incoming message, and the received version of the R and S. So if the quantity matches the R component of the signature, then the signature is validated. So this figure shows the mechanism for signing and verifying signature. Note that at the end the test the value of R, which does not depend on the message at all. Instead, R is a function of K and the three global public key components. The multiplicative inverse of K mod Q is passed to a function that also has as input the message, hash code and the user's private key. The structure of this function is such that the receiver can recover or using incoming message and signature, the public key of the user and the global public key. It is certainly not obvious that such scheme would work. So given the difficulty of taking discrete logarithms, it is infeasible for an opponent to recover k from R or to recover x from the S. So the elliptic curve digital signature algorithm, ECDSA in short, is enjoying increasing acceptance due to the efficiency advantages of elliptic curve cryptography. which yields a security comparable to that other schemes with a smaller key bit length. So first we give a brief overview of the process involved in elliptic curve digital signature algorithm. In essence, four elements are involved. So first of all those participating digital signature schemes use the same global domain parameters which define an elliptic curve and point of origin on the curve. Secondly, a signer must generate a public-private key pair. For private key, the signer selects a random pseudo-random number. Using that random number and the point of origin, the signer computes another point on the elliptic curve. This is the signer's public key. Thirdly, a hash value is generated for the message to be signed using the private key, the domain parameters, and the hash value, and a signature is generated. The signature consists of two integers R and S. Finally, to verify signatures, the verifier uses the inputs signer's public key, the domain parameters, the integer S, the output is a value V that is compared to R, the signature verified if the value V is equal to the value R. So this figure illustrates the signature authentication process. As you can see, the global variables are initiated and shared between the users. The sender B Bobs generates a private key D, public key Q, which is shared with the receiver Alice. Then the sender generates the K value and XY pairs and generate a OR value taking X mod N. So if the signature is 0, the process is repeated, and if it is not, it is formed using a hash function on the input message. And if it is 0, then the entire process is repeated again. If it is not, the signature of M is referred as RS. And this signature is transferred along with the public key and the message M. So the first thing, the receiver checks that the R and S integers are in range specified by the number N. If it is true, then if it is not true, the receiver rejects the signature, and if it is true, it calculates the hash value and checks whether it is a valid signature. So if it is 0, then the signature is again rejected. And finally, if you compare the value of V with the R, if the test passes, signature is accepted, otherwise the signature is rejected. So another algorithm proposed by the RSA probabilistic signature scheme, and was included in the 2009 version of FIPS 186. And latest of RSA schemes, and one of the RSA laboratories recommend as the most secure RSA scheme. Because the RSA based schemes are widely deployed in many applications including financial applications, there has been a great interest in the demonstrating that such a scheme are secure. For all schemes developed prior to this scheme, probabilistic uh, signature scheme, it has not been possible to develop a mathematical proof that the signature scheme is as secure as the underlying RSA encryption decryption primitive. The probabilistic signature scheme was approached first proposed by the Bellray and the Rogaway. This approach, unlike the other RSA-based schemes, introduces a randomization process that enables the security of the method to be shown to be closely related to the security of RSA algorithm itself. Before examining the algorithm, we need to describe the mask generation function known as MFG used for as a building block of that algorithm. MFG is a pseudo-random function that has an input parameter of a bit string x and any length of the desired length L in the octets of the output. Typically, MFGs are based on a secure cryptographic hash function such as SH1, and it is intended to be cryptographically secure way of generating a message digest or a hash or a variable length based on an underlying cryptographic hash functions that produces a fixed length output. The MFG function used in the current specification of RSA-PSS is MFG1. So it has the number of parameters such as a hash function on the outputs of h length octets, an input of x octet strings to be masked, and the mask length. The output is a mask generated of a length mask length. So the first stage of generating an RSA-PSS signature is a message M to generate from M a fixed length message digest called an encoded message EM. So this figure illustrates the process, and we have number of parameters here. First of all, we have number of hash functions. The current preferred versions of hash functions is SHA1. We have MGF mask generation function. So again, the current specification calls for MFG1. The S length is a length. Typically, S length is equal to H length, which is the current version of 20 octets. The input is a message to be encoded, referred as M, then EM bits is the value of 1 less than the bits of the RSA modulus n. The output is again EM is encoded message. The message digest will be encrypted in form of digital signature. There are some other parameters as well. EM length, the length of EM in octets, and the padding. The first padding is referred as padding 1, and it is a hexadecimal string of zeros of approximately 64 zeros. And the second padding, padding 2, is a hexadecimal string of 00 octets with the length around followed by the hexadecimal octet of value 0, 1. Two values, salt is a pseudo random number generator, and BC is the hexadecimal value of DC also incorporated. So we make several comments about the complex nature of this message digest algorithm. All the RSA-based standardization digital signature schemes involve appending one or more constants, padding 1 or padding 2, in the process of forming the message digest. The objective is to make more difficult for an attacker to find another message that maps to the same message digest as given message, or to find two messages that map to the same message digest. So RSA probabilistic uh, algorithm also incorporates a pseudo-random number, namely the salt, because the salt changes with every use. Signing the same message twice using the same private key will yield two different signatures. This is added layer of the security. So the EM verification can be described with a number of options. Again, it has hash function uh, with the output h length octet. It has a mask generation function and the input of m and the output of e, input of e m again. Then the parameters of the padding 1 and padding 2 are also added. So the algorithm starts with the generation of hash value of the message M to generate the hash value of that received message. The next step is to generate the mask DB to be the leftmost EM minus HL H length octets of EM, and let H be the next length of octets. So in this way you can calculate the mask by the mask generator function by providing the H and the mask dB and performing the exclusive OR function to produce the value dB. At this step you set the value of salt and the value of hash function and the padding to and fed it to a hash function to generate the final hash value. So here is the summary of the lecture. In this lecture we discussed about the digital signature, that how digital signatures are formed and what kind of attacks and forgeries are possible on digital signatures. There are different type of techniques such as Elgamal, Schnorr and NIST techniques were initially discussed. And finally, two more secure algorithm techniques such as elliptic curve digital signature and RSA-PSS digital signature algorithms were discussed. So if you want to read more about the topic, you can read the chapter number 13 of the recommended book, or you can conduct a question and answer session. Thank you very much.